We'll continue now looking at nonlinear systems and talk about rarefaction waves and integral curves. So in the last lecture, I talked about shocks and the Hugonio locus, the set of states you can connect to a given state with a shock wave. Now we'll look at a different set of curves, the integral curves, which allow us to determine the sets of states we could connect with a rarefaction wave, or more generally, talk about simple waves in a particular wave family. And again, we'll look at the shallow water equations as an example and talk about how we can then solve the general Riemann problem for the shallow water equations using this theory as well. And some other important concepts, more generally, the idea of genuine nonlinearity that generalizes convexity for scalar problems, the idea of Riemann invariants, and then also linear degeneracy and contact discontinuities. So again, the shallow water equations are written here at the top, and I've now called the momentum mu h times u, and it's also the flux of h in the first equation, and then the momentum flux I've written as phi, just to make it a little clearer that when we compute the Jacobian, we have to be careful that we're differentiating with respect to the two variables h and mu. But if we do that properly, then we get these eigenvalues and eigenvectors, which we'll be using in the examples. And what I've drawn here now is a set of curves in the phase plane, the HHU plane, that have the property that if you look at the tangent vector to any one of these curves, those are the arrows drawn here, each one of those arrows points in the direction of a corresponding eigenvector. So for example, at this point here, the tangent vector to the curve points in the direction of the eigenvector R1 evaluated at this particular value of Q. So at every point in the phase plane, there's an R1 eigenvector, and you can plot that sort of field of vectors and then draw lines that sort of flow along those directions. Or we can try to define curves that have the property that if we take parameterization of the curve, parameterized by some scalar value xi that's varying as we move along the curve, then if we look at the tangent vector, which is the derivative of q tilde of xi with respect to the two components of xi, that vector should be proportional to the eigenvector at the corresponding point on the curve. And alpha here would be some scalar, because we, of course, can multiply an eigenvector by any scalar, and it's still an eigenvector. And the actual sort of length of these tangent vectors will depend on the particular parameterization we choose. So for shallow water equations, a natural parameterization that we'll look at later is to take xi to be h, the depth of the fluid, or the distance along the horizontal axis here, because each one of these curves is sort of single valued as a function of h. So that's one possible parameter, but that's not the only parameter that one could choose. So these curves are very important because we can define what's called a simple wave that I mentioned a bit about last time. And the simple wave has the property that it's sort of things reduced to a scalar conservation law, and we're really just looking at changes in one characteristic family while the other family is essentially constant. So the idea in a simple wave is that the values of q always lie along one of these integral curves, some single curve for some particular family p. Shallow water p is either 1 or 2, and the curve would be one of these 4 curves shown, or any of the other curves. And then if we choose initial data that somehow lies on one of these curves, lies along a curve, it could be oscillating back and forth depending on what data we choose, then if we start with a smooth function, then it will remain smooth for a short time, and it will be a simple wave. So for example, we could take initial data that's maybe a hump in h. So maybe there's some background depth h0, and then it goes up to some maximum height h hat, and back down to h0 again. And if h0 were, for example, this value here, then as we move along here in depth, in order to get a simple wave, we would have to sort of move up and down along this curve and see that our HU also has to vary in a similar manner. So HU would have to, if this is H, then HU would be varying in a similar manner to the variation in H in order to be moving up and down along the same integral curve. And if we did that, these are integral curves of the second family, which correspond to the second eigenvalue u plus the square root of gh. And since here we're starting with u equals 0 and we have some slightly positive velocity, these are going to be waves that are definitely moving to the right. And so this would give us a simple wave which would simply propagate to the right. It wouldn't be completely unchanged in shape because of the nonlinearity, but if we took a small perturbation of h0, it would be unchanged or almost unchanged for quite some time. Eventually, it might steepen up into a shock followed by a rarefaction wave, at which point the solution would no longer lie along this single integral curve once a shock forms. But until a shock forms, even at a later time, if it started to steepen up, it would still be comprised of points that lie along this same single integral curve. And this is very similar to what we've seen for the linearized acoustics equations, where we saw that we could take, for example, a pulse in pressure, and then if we chose the velocity to be exactly the same shape but scaled by the impedance, then we would have a wave that was either purely in the left-going family or purely in the right-going family, and it would, in the linearized case, it would propagate with unchanged shape as long as we took that correct relation between the two. And that's a special case of this, where in the linear case, the characteristics are just straight lines, so you can move any distance up and down them, and you never have shocks forming, so the solution simply translates with constant speed in that case for all time. In fact, if you linearize the shallow water equations, you get a system of equations that's essentially identical to the acoustics equations, but for the linearized perturbation in depth and perturbation in velocity, and this reduces to that theory in that case. So again, in a simple wave, we have that the solution q of xt is always lying along a single integral curve. So that means that we can write q of xt as q tilde of xi, where xi is varying along, and q tilde of xi is defining a single integral curve. But the parameter value xi now has to be a function of x and t. And we can, as I just pointed out, we could sort of specify arbitrary initial data that lies along this curve, and as long as it's smooth, it would stay on this curve. But of course, we can't specify xi of x and t arbitrarily. That has to evolve according to the differential equation. So we need to check when this sort of solution actually satisfies the PDE. And since we're assuming things are smooth, we can look at the quasi-linear form here, and then we can, with this assumption here, we can calculate what dq dt and dq dx are. They both involve the derivative q tilde prime of xi, the gradient of q with respect to xi, but multiplied then by ct or cx respectively. And so if we now take these expressions and plug them into the differential equation, well, before plugging it into the differential equation, we have to compute f prime times qx. Well, f prime times qx is the Jacobian matrix multiplied by this qx that we computed up here. But now here's where we use the fact that the derivative q tilde prime of xi is proportional to an eigenvector of the matrix. That's what define these integral curves. And so because q tilde prime is a scalar multiple of an eigenvector, when we multiply that vector by f prime, that is an eigenvector, so that reduces to just the eigenvalue lambda p times whatever that eigenvector is. So that allows us to take this matrix times vector and turn it into just a scalar times a vector. And so now we can plug this into our PDE, putting it into qt plus f prime of q, qx equals 0. And what we end up with is that this scalar times the vector q tilde prime of c at xt has to equal 0. Okay, so now we end up with a scalar equation that this has to equal 0. It's now a scalar equation for the parameter xi, how it varies as a function of x and t, and it just looks like a nonlinear, quasi-linear scalar conservation law in which the coefficient here is lambda p, the eigenvalue. So I've got that again on the next page. So we end up with just this scalar equation. So assuming that q tilde prime is always proportional to an eigenvector, we can replace f prime of q by the lambda times q prime, and we get that scalar equation. And this is really analogous to this sort of theory we have for scalar conservation laws. And it says that the solution remains constant along characteristic curves, and the characteristic curves are x prime equals lambda p evaluated at q tilde of xi, as long as the solution stays smooth. This is like our scalar equation where we had qt plus some f prime of qx equals 0, but in the scalar case, where f prime of q is just a scalar, then we had the solution was constant along characteristics, and as long as the solution stays smooth, as long as the characteristics don't start to cross. And it's exactly the same thing here, except that in this case, in the nonlinear case, once the shock actually forms, we don't stay on the same integral curve in general, and waves in other families can be generated as the shock forms. So it gets a little more complicated in that case. But at least as long as things stay smooth, we have a sort of a nice simple wave that can be reduced to a scalar equation in a single wave family. And in particular, if we look at the case of a centered rarefaction wave, so this means that we're starting with some initial data that's discontinuous at time 0 from QL to QR, and then for larger times, we're assuming it's a similarity solution, so the solution should be a function of x over t, and it's as in the scalar case, it's going to be constant along rays from the origin in this scalar conservation, or in the xt plane, we've got QL and QR here, and then along each ray from the origin, the solution should be constant, and it's a similarity solution, so it's q tilde of x over t. And it turns out you can find centered rarefaction waves like this as long as QL and QR are on the same integral curve, and as long as lambda p at QL is less than lambda p of QR, because those are the speeds of the left edge and the right edge of this rarefaction fan. And so in order for this to make sense physically, we need the eigenvalue increasing as we go through this rarefaction wave. So this is really a special case of a simple wave, as we were just talking about, except now this parameter xi as a function of x and t, we're expecting to be just x equal to x over t, because we want our solution to be a similarity solution. So if we plug that assumption into this scalar OD or scalar PDE that we were just derived on the previous slide, then when we differentiate xi with respect to t, we get minus x over t squared. When we differentiate it with respect to x, we get 1 over t. And so this equation then becomes this, which if we simplify it a bit, we can write as lambda p of q tilde of x over t has to equal x over t. In order for the solution to be a simple wave, it has to satisfy this, but we want it to be not just any simple wave, but a simple wave in which the parameter xi is varying in this self-similar way. So we can think of that as we need to solve this equation, lambda p of q tilde of xi is equal to xi for xi as a function, or for q tilde rather, as a function of xi, and that will tell us how the solution varies through the rarefaction wave. This is exactly the same as what we saw for the scalar conservation law case, where the corresponding equation was that just f prime of q tilde of xi has to equal xi in order to solve for the structure of a rarefaction wave in Berger's equation, for example, or traffic flow. And this is exactly the same condition. In the scalar case, of course, there's f prime is equal to the eigenvalue. There's only one eigenvalue in the scalar case, and so it's exactly the same equation. And again, this requires that to have a physically meaningful centered rarefaction wave, we have to have these characteristics spreading out. So we need lambda p at q left definitely to be less than lambda p of qr. But moreover, we know from looking at scalar conservation laws that we need something a little stronger than that. We really need not only that the value in q left is less than q right, but we also want it monotonically increasing in between. That's what we call convexity in the case of a scalar flux, so that the solution is increasing monotonically as we go through this rarefaction fan. Otherwise, if it's not, then you get into this more complicated case where there might actually be a shock embedded within the rarefaction wave, or some combination of shocks and rarefactions in the non-convex case. And similarly, for a system of equations, if you don't have this monotonicity, then you can have more complicated structures where a single Riemann problem might have compound waves that involve both shocks and rarefactions in each of the nonlinear families. So this is what we call genuine nonlinearity for the system case. Again, remember in the scalar problem, the analog is convexity, and the idea was that we wanted f prime of q, which is the characteristic speed, to be monotonically increasing, which means that the second derivative has to be positive, or monotonically decreasing, in which case the second derivative would be negative. But it has to have the same sign everywhere, at least for the set of q that are of interest. And now for a system of equations, what we need is that for a particular wave family P, we want lambda P of Q to be monotonically varying along the integral curve corresponding to that component. In other words, the curve that's always tangent to the eigenvectors Rp that go along with the eigenvalue lambda P. If so, then we say that this field is genuinely nonlinear. And it could happen that in a system of equations, some fields are genuinely nonlinear and others aren't. And I'll talk about such a case later on. But for shallow water equations, it turns out both fields are genuinely nonlinear. They have this analog of convexity. So what does this require for a system? Well, we want the derivative of the eigenvalue evaluated at some q tilde of xi as we move along one of these integral curves. We want the derivative of that with respect to xi to be either always positive or always negative. And if you calculate what that derivative is, well, that's the gradient of lambda dotted with the gradient of q tilde of xi, which I've called q tilde prime of xi. So we need that inner product to be always positive or always negative. And so just like we sort of summarize f prime being monotonically increasing or decreasing by saying that the second derivative should never be zero, similarly we can say that here this quantity on the right should never be zero in the region that we're interested in. That way it's always positive and lambda is increasing, or it's always negative and lambda is monotonically decreasing. So here's a picture for the shallow water equations, where the magenta line, I guess this is the one particular integral curve of R1. So any one simple wave or one rarefaction wave would have states that lie along this magenta curve. And then the green curves are contours of the eigenvalue lambda 1. So at each point, we have an eigenvector R1, which is pointing tangent to this curve, and then we have a corresponding eigenvalue. And what we see here is that as we move along this curve, the eigenvalue is monotonically decreasing in this case. Lambda 1 starts out at 2 along this curve, it's 0 here, it's -1, -2, and as we go along this curve, wherever we start and stop, if we keep moving in the same direction, lambda is monotonically decreasing. So by the way, if we had a case where lambda wasn't monotonically decreasing, maybe I can just draw in here such a case. So suppose that we had contours of lambda 1 that instead of looking like that, look something like this. Here's a contour that maybe corresponds to lambda 1 equals 0, and then here's maybe a contour where lambda 1 equals 1, and then another contour where lambda 1 equals 2, and so on. Another contours down here where lambda 1 equals -1. Suppose those were our contours. Well, then as you move along this curve, lambda would be -1 here. Whoops. Lambda would be -1 here, but then would increase until you get to this point, and then it would start decreasing again. So in that case, if those were our contours, then lambda 1 would not be monotonically varying. And the point where it reverses direction is right at this point where the contour of lambda is just tangent to this line. So sorry, let me draw this again. So if we had some contour of lambda, some particular value of lambda that happened to be just tangent to this curve at some point, then you would see that as you move along the integral curve, lambda would be first decreasing and then increasing, or vice versa. Well, at a point like this, the eigenvector is tangent to the curve, and the gradient of the eigenvalue is always orthogonal to the contour lines. So the gradient of lambda would be orthogonal to the eigendirection at such a point, and so their inner product would be 0. And so this condition that it's genuinely nonlinear says that the gradient of the eigenvector can never be orthogonal to R1, and so we can't have that sort of situation. So for the real picture here for shallow water equations at a point like this, so for the real picture for the shallow water equations at a point like this, the eigenvector is pointing in this direction, and the gradient of lambda is pointing in a similar direction, and they're definitely not orthogonal. And we have this condition that gradient of lambda inner product with the eigenvector is not equal to 0 everywhere along the curve. So we can also go ahead and compute this for the shallow water equations just to check that that's actually true in general. And again, here's what the eigenvalues and eigenvectors are. And so if we check this condition now, we can evaluate from lambda 1, and again I'm going to write lambda 1 in terms of the two conserved quantities, q2 divided by q1, that's hu divided by h, and square root of g q1, so that I can compute the gradient of lambda properly by differentiating with respect to q1 and then q2, and then you can simplify it to the form over here on the right in terms of our h and u, and similarly the eigenvector r1, which we've seen before, and now you can just take the inner product of those and confirm that the inner product is always, it's -3/2 times the square root of g over h. So as long as h is positive, fluid depth is positive, that's always strictly less than 0, and this field is genuinely nonlinear. And the second family is as well. Okay, so now let's look at how we would actually compute these integral curves. As I've said, they're curves that go through phase space that are parameterized by some parameter c. How would we find them? Well, we know that the derivative q tilde of c has to be some scalar multiple of the eigenvector, r1 in the case of the integral curves of r1, for some scalar function alpha of c. And in terms of sort of solving for what these curves are, we're free to kind of parameterize as we want to. And an easy way to do it often is just to suppose that alpha equals 1 so that we simply use the eigenvectors in whatever form we've written them down in as the right-hand side of this differential equation. So we have that the q1 prime is the first component of the eigenvector, q2 prime is the second component of the eigenvector. And so that gives us a system of two ordinary differential equations. And the first equation here just says that q1 prime is equal to 1. So q1 is, we can just take as xi, but q1 is, the first component of q is just the depth. And so this suggests that with this particular scaling, we're going to be essentially taking a parameterization in which xi is the depth h, as I indicated back at the beginning, would be a possible parameterization of these curves. So as xi varies, h is just equal to xi, but now the real interesting part is how does hu vary now as a function of xi, because that allows us to draw these curves of how hu varies with respect to h on each of the integral curves. So the second equation from the ODE system, if we simplify that a bit, can be solved to give this expression here, that the momentum, the q2 component as a function of xi, turns out to be, if we choose a particular point h star and h star u star, again there are these integral curves for whole family of integral curves, so we want to choose a particular one, so we'll choose one particular point, say h star and h star u star in the phase plane. And now we're looking for the integral curve that goes through that point. And the xi parameter will be h varying on the horizontal axis, and this tells us how hu has to vary as h varies then. And we get an expression that looks like this. Or if we rewrite things in terms of h and u again, we end up with these expressions for the two integral curves. For the one-wave curves, the momentum is just h times u star, whatever point we chose, plus 2h times the difference between square root of gh star and square root of gh. And that holds for any h between 0 and infinity. So that gives us, if we plot this, if you fix h star and u star and plot this as a function of h, that gives you exactly one of these integral curves for R1. And similarly, you can go through the same computation for two waves, where we use the R2 eigenvector instead of R1, and you end up with a very similar expression, just as a minus sign here instead of a plus sign, and that's what gives you this other set of curves, the two-wave integral curves. And as I mentioned in the last lecture, we looked at the Hugonio loci, which, remember, are the set of points you can connect to a given point. So if this point here is supposed to be, say, our q star, some particular h star and h star u star point. If we look at all of the points that can be connected to that point with a shock wave, or at least a discontinuity that satisfies the Rankine-Hugonio conditions, whether or not it's a physically correct shock wave, if you look at that locus of points, that gives you the Hugonio locus, and those are the curves in red and blue here. But now we can also look at the two integral curves with the formulas we just derived going through this same point, and that gives us the magenta and green curves. Sorry, the colors didn't show up in the legend for some reason for those, but the magenta curve is the one wave integral curve, and the green curve is the one wave, or the two wave integral curve, and they're very close to the one wave Hugonio locus and two wave Hugonio locus, particularly around the point q star, but they deviate more and more as you get farther away. So if we want to solve a Riemann problem for the shallow water equations, if we now have two states, q left and q right, then if those two states are here and here, and I'm not saying which one is q left and q right, which one is q right, but depending on which one is which, we would want to find an intermediate state that goes first from QL along a one-wave curve to some middle state, and then from that point along a two-wave curve to get to Q right. So if this, for example, were Q left and this were Q right, then we would want to go along one of these two curves to some middle point here, and then along this curve here. So our QM would be somewhere here, but there's still four sort of possible intersection points depending on which one of the curves we follow. And so then we have to use the fact that we know that a shock wave is appropriate if the characteristics are going to be converging on the shock, whereas a rarefaction wave is appropriate if the characteristics are going to be spreading out. And if we switch Q left and Q right, then it would be the other intersection points that would correspond to the solutions. So as a concrete example, let's look again at this dam break problem where we have a jump in h, but the velocity is 0 on both sides initially. And what we've seen is that you then get a shock wave moving to the right and a rarefaction wave moving to the left in that case. And so if we know that we should have a 1 rarefaction and a 2 shock, then we know that this intermediate state we're looking for has to lie on an integral curve for one waves, curve that's always tangent to R1 going through QL, but it also has to be on a Hugonio locus corresponding to two waves that passes through QR. And so we would have to find the intersection of those two curves. And again, those two curves, well, one's a one wave and one's a two wave, but they're also, one's an integral curve, one's a Hugonio locus. So the two formulas look somewhat different. The one on top is for the integral curve that we derived a moment ago. And this is for the Hugonio locus going through the right state, which we derived in the last lecture. And so we need our point UM to lie, to satisfy both of these equations. So if we just equate them and eliminate this UM, we can boil this down to a single equation in which the only unknown now is HM, which appears here and here. We know UL, HL, UR, HR. I guess HM also appears here. So we have a nonlinear equation that in general we can't solve analytically, but it's a scalar nonlinear equation, and you could use Newton's method or any other root finding method to find a solution. And you could use something like the two shock solution, which was easier to derive as an initial guess for what the intersection point is. And when we were talking about the Hugonio locus, we also saw this figure where this was, if we look at a state QL here, then this is the one wave Hugonio locus, and the solid part is the set of states we can actually connect to a shock wave that's physically correct. The dashed line are states that you can connect with a jump satisfying the Rankine Hugonio conditions, but it wouldn't satisfy the entropy condition. It should be a rarefaction wave instead. And so these are the one wave shocks have to lie along this curve, but over here we should really take this dashed line and replace it by a slightly different curve, namely the integral curve that corresponds to rarefaction waves. And similarly, if we look at the right state, QR, and we look at two waves, well, if we go off in this direction, then we can connect QR to some middle state that's actually to the left of QR physically by a shock wave if it lies in this direction. But in the other direction where the line is dashed, we don't want to use a shock wave, and so instead of using that dashed line, we would replace that by the corresponding integral curve, which again looks very similar but doesn't lie right on top of it. And so if we took these sort of composite curves that consist of the integral curves here and here, and the shock Hugonio curves here and here, then we could plot these together and look for the intersection points, and we would find the correct physical solution of the Riemann problem. So that's what's suggested in the book in section 13.10, that we can, for general QL and QR, we can define two curves, and I guess I've written these in terms of u's rather than hu, but the idea is that again, this phi L of h for a particular point HL, this is the equation for integral curves, which we use to the left of HL, and this is the equation for the Hugoniot locus, which we use if h is to the right of HL. And similarly for two waves, we either use this equation if h is less than HL, which is the integral curve, or this equation if h is greater than HR, which is the Schoch-Hugoniot curve. And then what we want to do, this gives us all possible states that could be and we want to be equal at the intersection point, and so we can subtract phi L of h minus phi R of h to define some function phi of h, and then use a root finder to find the zero of phi of h, and that allows us to determine the intermediate state HM that solves the Riemann problem with the correct Schoch or rarefaction in each family. So you can do it all in one fell swoop here, because we can easily, based on the original data for shallow water equations, at least you can easily decide whether you're in the Schoch or rarefaction case for each of the two waves based on where you are relative to those states. Okay, so just want to mention a couple of other concepts before we break this time. So one is the idea of a Riemann invariant. And if we go back to the expression we were just looking at for the integral curves, for example, this top expression here for an integral curve, we see that along an integral curve, this relation is satisfied that u is always equal to u star plus twice square root of gh star minus square root of gh. So this is the integral curve that goes through some particular h star and h star u star in the phase plane. But if we rearrange this a bit, it says that u plus the square root of 2gh is equal to u star plus 2 times the square root of gh star. So on the right here, this was one particular point on our integral curve, but on the left we have any other points on the integral curve. So that's actually telling us that u plus 2 square root of gh is constant everywhere on the integral curve. It has to be equal to the value at any particular point. And so this quantity u plus 2 square root of gh is constant on integral curves for the one family, and so it's called a one Riemann invariant. So another way to look at this is that this function w1 of q is constant along each integral curve. It has different values on different integral curves, and so the integral curves are actually contour lines of this function w1 of q. So another way to plot all of or a large set of integral curves would be to choose some region in phase space and discretize it on a uniform grid that's fairly fine, evaluate this function w1 at every point on the grid, and then make a contour plot of w1 of q. And the contour lines would be good approximations of the integral curves corresponding to R1. And similarly, there's a set of two Riemann invariants, which are constant along the two-wave integral curves. Look exactly the same, except with a minus sign instead of a plus sign. And so again, we could look at the two-wave integral curves as being simply the contour lines of this function wq in the phase plane. And then finally, I'd also like to mention the concept of a linearly degenerate field. So we talked about a genuinely nonlinear field, which is the analog of a convex scalar problem. A linearly degenerate field is kind of the other extreme. It's the analog of a linear scalar problem, like the scalar advection equation with constant coefficients, for which we know the characteristics are parallel. And so if you can have a discontinuity in the solution. If we look in the xt plane, you can have a discontinuity that travels at some speed. S is simply equal to u in the advection equation. But if we draw characteristics, they would be parallel to that. And so it may be a discontinuity. If you start with discontinuous initial data, it will simply propagate along that line. And it satisfies the Rankine-Hugoniot condition for this linear flux function. But it would be wrong to call it a shock wave because we reserve the term shock wave for the case where the characteristics are impinging on discontinuity. So it's a linear discontinuity that's propagating in such a way that all the characteristics are going parallel to it. So in a system of equations, of course, a linear system, if it's a fully linear system, qt plus aqx equals 0, it has the same property in every characteristic field. But you can have nonlinear problems for which this sort of thing holds in some fields, but not in others. And in the scalar case, here for the advection equation, f of q is just uq, so the derivative is just u everywhere, and the second derivative is identically 0. So we can have sort of something comparable happening in the system case. So in the system case, we said that it was genuinely nonlinear if this inner product of the gradient of lambda with the eigenvector was never 0. But if instead it's identically 0, then it's more analogous to the second derivative of the flux being identically 0 in the scalar case. Because in that case, the derivative of lambda p along one of these integral curves, it's again the inner product of the gradient of lambda with the derivative of q tilde of c, our parameterization. Q tilde of c is our parameterization of the integral curve, and the derivative is an eigenvector. And in this particular case, if that inner product is always identically 0, then that means that the derivative of lambda is 0 along the integral curve, and so lambda is constant along the integral curve, just like f prime of q is constant for the scalar advection equation. So if this holds, then we say that the P field is linearly degenerate. So it's acting like a linear problem. It's sort of degenerate in that it doesn't have any variation at all in lambda along the integral curve. So this is one extreme. The other extreme was where this inner product was always non-zero for all q on the integral curve. There can, of course, be intermediate things which are more like non-convex but nonlinear scalar equations, but the simplest ones sort of inherit these kinds of properties that we saw in the scalar case. So we've already seen sort of an example of this dam break problem we've looked at for the shallow water equations repeatedly. In the figures, I've used color to indicate the motion of the fluid, so that red is what was initially to the left of the discontinuity, blue initially to the right. But the equations I wrote down here were only the fluid dynamics equations, and I didn't put in an equation for how color would be transported. But we can add to this system of shallow water equations, we can add another equation for some tracer that's actually measuring the color of the fluid, and then we could put in something that varies in such a way that you can actually generate these kind of patterns of how the solution is behaving. So to do that, we can add another quantity phi, tracer concentration, and add the color equation that says that phi should be constant along the particle paths. So phi t plus u phi x equals 0. Although this color equation is not in conservation form, to kind of incorporate this into the conservation laws, we can use the first equation of the shallow water equations and combine it with our color equation, and from that you can derive a conservative form of the advection equation here for phi, that the time derivative of h phi plus the x derivative of uh phi equals 0. If you just use the product rule on that and use the first equation of the shallow water equations, you can reduce that to the color equation. But that puts it in conservation form so that we can now express a system of conservation laws with 3 equations for h, hu, and h phi, and the flux then is the fluxes of shallow water equations augmented with this flux from the advection of phi. or rewriting it in terms of Q1, Q2, Q3 to make sure we do things properly when we compute the Jacobian. We can now differentiate with respect to each of the three variables, Q1, Q2, and Q3, and we end up with a 3×3 Jacobian matrix. And if you work that out and then simplify things to rewrite it again in terms of H and U, you get this equation for the Jacobian. And if you notice, this is a sort of a block structured matrix. We have a 2×2 block up here, which is exactly the Jacobian of the shallow water equations. And then we have U, this additional eigenvalue that comes from the advection equation that we added. And because these are zeros in this column up here, this we can look at as sort of a block diagonal matrix with a 2×2 block and a 1×1 block. And the eigenvalues of such a matrix are just the eigenvalues of the 2×2 block, which are the usual eigenvalues of the shallow water equations. And then the eigenvalue of the 1×1 block is just U, which is what we would expect, that the additional advection equation adds another characteristic speed, which is the fluid velocity itself. And you can easily work out the eigenvectors for this system as well. And you find these eigenvectors corresponding to the eigenvalues. And R1 and R3, the first two components are just the usual eigenvectors of shallow water equation, but they have another component added. And then the R2 eigenvector is the new one that goes along with our new eigenvalue U, which is always between λ1 and λ3. And R2 has the structure that the first two components are 0 and only the last component is a 1, which means that a wave in this family corresponds to a jump in phi, but no jump in h or hu. So as we expect, since this tracer is not supposed to be affecting the fluid dynamics at all across the wave that is modeling the tracer motion, there's no jump in depth or momentum. There's only a jump in the value of phi. And we can check that that intermediate wave family is linearly degenerate if we calculate λ2 is u, which we can write as hu over h, and then if we take the gradient of that, differentiating with respect to h, hu, and phi, we end up with this vector. And then if you take the inner product of that with R2, this vector up here, what you get is identically 0. And so that shows that this second field is linearly degenerate, whereas the fields 1 and 3 are essentially exactly the same as in the shallow water equations. There's no variation in phi. There's only the variations in h and hu following the usual shallow water theory. So if we look at the solution of the Riemann problem that we had a moment ago, this sort of Riemann problem here, if we looked at this in the xt plane, we have a rarefaction wave that's moving to the left and a shock wave that's moving to the right, which are exactly what come out of the shallow water equations. But then there's also this linearly degenerate field that is the displacement, or the jump between red water and blue water in this case, that's moving in this case with positive speed at some intermediate speed here. And so those would be sort of the structure of the Riemann solution. We'd have q left and q right over here. And in the intermediate states, h and hu would be the same in both of these regions on both sides of this contact discontinuities, it's called in this case. It's where the two initial fluids are in contact with each other. And the values of h and hu would be the same across that. There would only be a jump in phi across that contact discontinuity that would be moving with the fluid velocity. So it's being carried along with the velocity of the fluid. And the fluid on each side is constant, is the same value. The fluid velocity on each side is the same value. And so the characteristics, if we drew the characteristics for this family, they would be parallel to this contact discontinuity on both sides of the contact discontinuity. They would, of course, the characteristic speed u starts out being 0 in the right state, but then it jumps to this non-zero value across the shock. Starts out being 0, u is 0 in the left state, but it smoothly accelerates towards this intermediate velocity as you go through the rarefaction wave. So that would be the structure of the Riemann solution for this problem. Yeah, and so again, in this problem, the second field has this linearly degenerate property, whereas fields 1 and 3 are genuinely nonlinear. And also when we look at the Euler equations of gas dynamics, where we then have three conservation laws for mass, momentum, and energy in general, it turns out that it has a very similar structure, that there are two, the one waves and three waves are genuinely nonlinear and sort of correspond to nonlinear acoustics waves, but the wave in between is a contact discontinuity. It's more complicated than just being a jump in some tracer, but there can be a jump in density while the velocity and the pressure are the same on both sides of it. So we'll look at that in more detail when we look at gas dynamics and the Euler equations.